Hello everyone, sequence, series, and proof, day number 4. Topic of today is direct proof. Direct proof is a way of showing the truth of a given statement by constructing a series of established facts. Basically, you're going to use what we know as foundational facts in order to show equivalence. Many times you'll have an equation, and as you can see down here, you would choose one side only. If you work both sides of an equation at any given time, that is an invalid proof. So let's try a few examples. Okay, so let's look at a couple of examples here. We're going to show that the sum of all the odd numbers infinitely equals n squared. So I'm going to work on the left-hand side. Typically, the left-hand side is set up in order for you to work that to show that the right-hand side is the result of the left-hand side. So I'm going to take the left-hand side, which is 1 plus 3 plus 5, and actually I'm going to add in a term before the last term that we have present, which is 2n minus 3, which is 2 less than 2n minus 1, which is true of odd numbers and even numbers, right? They're two numbers apart. And I'm actually going to add it. I'm going to call this the sum of the first n terms. And I'm going to add it to the sum of the first n terms in the opposite order. So it'll be 2n minus 1 plus 2n minus 3 all the way out to then 3 and 1. We did this in the proof of the sum of the first n terms of an arithmetic series in order to show its general formula. But what I get here is 2 times the sum of the first n terms. And what you'll notice is as we add the first terms together, we get 2n. And the same thing as we add the second terms, all the way up to when we add the last two terms. And what's cool is that there are two n's. Therefore, 2 times the sum of the first n terms is equal to n 2n's, which means that 2 of the sum of the first n terms, or twice the sum of the first n terms, is 2n squared. So if twice the sum of the first n terms is 2n squared, then what would be the sum of the first n terms? It would be n squared. And there we have it. We've shown the right side equivalence. Okay, so by a direct proof method, I now know that this equation is true. Okay, let's look at part B. The sum of an odd and even positive integer is odd. Well, by definition, an even number takes on the form 2m, where n is the even integer and m is in z plus, which is the set of positive integers. An odd number, let's call it q, is equal to 2 times p plus 1, where p is a positive integer as well. Okay, so actually, excuse me, let me correct myself. It's not a positive integer, it's an integer such that p is greater than or equal to 0. Because if p equals 0, then q equals 1. Okay, so the sum of an odd and even integer. So let's take n plus q. And we want to show that that's odd. Okay, so n is 2m, and q is 2p plus 1. So if I combine those first two terms by factoring out a 2, I get 2 times the quantity m plus p plus 1. And this fits the definition of an odd number, right? So let me define a new odd number, w, and let's say that w is 2 times x plus 1, right? So x must be then in the integers with x greater than or equal to 0. Well, this fits the mold since m plus p is also in the integers, and specifically here because m is in the positive integers, then this would also, m plus p has to be in the positive integers. Then we can say by direct proof that n plus q is therefore odd. Okay, let's look at part C. The sum of two odd integers I actually made a mistake here. I need to change this on my notes, is even. All right, so two odd integers. Let's call them x, which equals 2t plus 1, and I don't know, let's call one y, which is 2w plus 1, where t and w are in the integers with t greater than or equal to 0 and w greater than or equal to 0. So the definition is important. Now we do the proof. Okay, so x plus y. Now in this case, we're going to work the right-hand side based on how I've set this up. I'm going to work the right-hand side, which is 2t plus 1 plus 2w plus 1. If I combine like terms here, or at least get terms that look similar near each other, so 2t plus 2w plus 1, which is 2, I can see that x plus y, again, just working the right side, is 2 times the quantity t plus w plus 1. This fits the original definition when we said that n equals 2m, with m, that should be an m, in the positive integers, right? So that was true if m was in the positive integers. Well, is t plus w plus 1 in the positive integers? Yes. So since t plus w plus 1 is in the positive integers, then x plus y is therefore even. All right, let's keep moving. Okay, so here we have an infinite summation. I see I have an alternating series here. Every other term is the opposite sign as the term before it. And I'm trying to show that it equals, in sum, 1/3. So I'm going to work on the left-hand side, and I'm going to show that when reduced or simplified, it equals the right-hand side. So the way to do a problem like this is to take, in this case, the positive terms, which we can see 1/2 plus 1/8 plus 1/32, added in an infinite way, would fit the summation model 1/2 times 1/4 to the I minus 1. Okay, this is a geometric series with a common ratio of 1/4 and a first term of 1/2. So the summation, using the formula that we know to find a convergent geometric series, will be the first term over 1 minus the common ratio. So therefore, this summation, 1/2 over 3/4, comes out to be 2/3. Okay, so I'm working the left side. I know that my red terms added up forever will be 2/3. If I can find my blue terms, that summation, I'm trying to show that that sum, red plus blue, equals 1/3. Let's check it out. So I've got -1/4. That's my first term. Looks like minus 1/16. And I'm guessing, based on what I see here from my first few terms, is that my common ratio will be also 1/4. So I equals 1 to infinity, -1/4 times 1/4 to the I minus 1. So this sum, if r equals positive 1/4 and my first term equals -1/4, the summation to infinity will equal the first term, -1/4, over 1 minus the common ratio. I believe that comes out to be, oh boy, is that going to be, that'll be -1/4 over -3/4, which comes out to be a -1/3. So if I take 2/3 and add a -1/3, look at that. I've shown, working the left side, that the summation of the red series and the blue series, which combines to make an alternating series, ends up equaling 1/3. Okay, when you get a proof or prove that for a statement like this algebraically, what you're going to do is you're going to identify which side you'd like to work with, Typically, you want to pick the more complex side or the side that has more going on. I'm going to pick the left-hand side, so I'm going to work that left-hand side. Okay, and I'm going to show through a process of algebraic steps that are known to me that it ends up equaling the right-hand side. So let's work the left-hand side. I'm going to FOIL out the first term. That'll be a squared plus 2ab plus b squared. FOIL out the second term, a squared minus 2ab plus b squared. We'll notice as we add these together, these two terms will reduce. Like terms are combined, they disappear, and I get 2a squared plus 2b squared, which when I factor out a 2, comes out to be 2 times the quantity a squared plus b squared. And there it is, proof, done. Okay, we can check that. That's a pretty basic example, but it's an example that shows that direct proof can be straightforward. Okay, at times it might be more complex, but for the most part, it can be straightforward. Okay, so last example for this set of notes. It says prove that if the sum of the digits of a 4-digit number is divisible by 3, then the number is also divisible by 3. So let's take a 4-digit number, 4298, right? What I'm going to do is I'm going to define the first digit as A1, the second digit as A2, the third digit as A3, and the fourth as A4. Now A1 isn't really A1, it's A1 times 1,000, right? So you can think A1 times 1,000. Because that is the thousands place, right? A2 times 100, A3 times 10, and A4, okay? All right, so keep that in mind. We're going to call those P and Q and R and S, all right, where it looks like our numbers A2, A3, and A4 have to be between 0 and 9, but can be 0 and 9. Now, the one number that matters that can't be 0 is A1, otherwise it won't be a 4-digit number. Okay, so A1 will be between 0 and 9, but can't equal 0. Okay, so just some logistics there. Let's get down to the proof part. So it says, prove that if the sum of the digits of a 4-digit number is divisible by 3. So the sum of the digits, not the digit itself. So the sum of the digits would be A1 plus A2 plus A3 plus A4 is divisible by 3. That means I'm going to define M in this case as an integer. Okay, so the sum of the digits is equal to 3 times some integer. That is the definition of being divisible by 3. Okay, so from here, what I'm going to do is I'm going to try to find a way to link this to the actual number. Okay, I'm going to link it to the actual number. And I've started the process right over here. Right? I have a way to link it. Now, wouldn't you say that P plus Q plus R plus S is equal to A2, this is not times, A3, A4, right? That's that number. That is that number. And actually, I should get rid of those multiplication symbols in there. Right? That is just going to equal the actual number. A1, A2, A3, A4. Okay, so if I can show that P plus Q plus R plus S is divisible by 3, then we can then determine that the number itself is divisible by 3. So this is the number. So let's do a little proof. P plus Q plus R plus S is equal to 3W, where W is in Z. All right, so P, what is P? P is 1,000, A1. Q is 100, oops, too many zeros, A2. R is 10A3, and I don't want to just plug in A4 because I might have some issues. What I'm going to do is I'm going to use, and you'll see this is true in math induction later on, I'm going to use what I know. You always want to use what you know. So I'm going to say that A4 is equal to 3m minus A1, A2, and A3. Now I'm going to do a substitution in for S, which is equivalent to A4. Therefore, I will plug in plus 3m minus A1 minus A2 minus A3, and I want to show that this is equal to 3w. Okay, so as I go, I'm going to combine like terms. You can see that I have like terms here with A1 and A1, A2 and A2, A3 and A3. So combining like terms, I get 999 A1 plus 99 A2 plus 9 A3 plus 3m is equal to 3w. I want to show that this expression is 3 times some integer. So I'm going to factor out a 3. That gives me 333 A1 plus 33 A2 plus 3A3 plus m. Now, since I know that A1, A2, A3, and m, are in the positive integers, then 333 A1 plus 33 A2 plus 3A3 plus m is in the positive integers. Okay, thus P plus Q plus R plus S is divisible by 3. Well, I'm struggling to write here, and therefore our 4-digit number, we can call it, let's call it F. Let's define our 4-digit number as F is divisible by 3. All right, guys, that's it for direct proof, day number 4. We'll see you in the next video, which will be proof by contradiction.